Welcome to the fourth week of live interactive session on the course Engineering Mechanics. So today's topic is friction. So I hope you have already watched the lecture videos for this week on friction. So we'll start solving some demo problems. So we have the first question, starting from the basics. So a block of mass 2 kg rests on a rough inclined plane making an angle of 30 degree with the horizontal. The coefficient of static friction between the block and the plane is 0.7. The frictional force on the block is. So we have options given. 1g, where g is the coefficient of gravity value, 9.81. It's not substituted, so it's 1g, 2g, 3g, 4g newtons. So which one would be the correct answer? So you can try solving this. It's actually from basic things only, so it should be easier to do. So I'll give you some time for try this out, and then I will explain how to do this. So if you found the answer, you can let me know. So we will discuss whether that's correct or not. So did you find the answer? Okay, let me explain. So already the resolution of force, everything is given in this picture. So I will anyway do it once again. So basically we have a block of mass 2 kg. So m is 2 kg, which is resting on an inclined surface, inclined plane, with the angle theta being 30 degree. So first of all, we have to check whether this be in equilibrium or not. So there is an angle of inclination above which this body will start to slide down, which depends on the surface friction. So here the coefficient of friction, static friction, is given as 0.7, and when it starts, the critical angle above which the body starts to slide, which is determined by the critical value of theta, which should be tan inverse of 0.7, or tan inverse of the friction factor, the friction coefficient mu(s). So here it is tan inverse of 0.7. So if you evaluate that, it will be 34.99, approximately 35 degree. So this is a critical value of angle above which this body will start to slide. But here it's given that the angle theta is 30 degree only. So that means this body is not yet started to slide down. So it's still in equilibrium. So when it is in equilibrium, now we can resolve the forces acting on it. So its mass is acting as a weight mg vertically downwards, and from between the inclined surface and its bottom surface, there will be a reaction force acting on the surface of the body. So these are the external forces acting on the body, two of them. And now because we are now in friction, so earlier we used to neglect the friction, but now we cannot. There's one more force going to act on the system, which is the friction, basically, which is balancing the body to not slide down, which is anyway acting on the bottom surface along this line, which is the frictional force F. So we are asked to find what is the frictional force F. So now if we resolve the forces, so the along the inclined surface and perpendicular to the inclined surface. So if you just draw the free body diagram of this body, the forces acting on it is mg is acting vertically downwards, and a normal reaction is acting perpendicular to the body surface, and a frictional force is acting parallel to the body surface. So I am taking a coordinate system which is along the body surface x and perpendicular to it y. So if I now see, the reaction force R is vertically acting in the y direction, and the frictional force F is acting in the x direction, but the force mg is not acting along any of these directions, inclined force. So I can resolve this into its components in the two directions. So if I do that, so if you see here, this angle is going to be theta. I think that's obvious for you to say that that's the angle between mg and r is indeed theta. So if it is not, you can just let me know, so I will tell how it is theta, or I think I will explain how it is theta. So if you draw a horizontal line like this, now this angle should be theta, right? Because this and this are parallel, so the angle which is made by this inclined surface, which is cutting through this both parallel surfaces, the angle it making with the both the surfaces should be identical, that is theta. Now if that angle is theta, and this angle should be 90 minus theta, because this mg is acting vertically downward, so that this theta plus, let's say, this unknown angle, both should contribute to the 90 degree, so that the unknown angle, the question mark, is actually 90 minus theta. Now if you think of this particular angle, that also should be 90 degree, because R is a normal reaction acting on the surface. Now this unknown angle we have found it is 90 minus theta, and that angle plus the angle here, which should make to total 90 degree, so that this angle should be theta. That's what I wanted to say. So I think that's clear now. So what is the conclusion is that the angle between the load mg and normal reaction R should be theta. So I mean, which is same as the inclination of the plane. So if this angle is theta, its component forces mg cos theta will act along the normal reaction direction, y direction, but in the opposite sense, and mg sin theta will be acting along the x direction, or in the opposite sense. Now at equilibrium, so because the body we found it to be in equilibrium, because the angle is still less than the critical value, so that the friction still valid and it is opposing the sliding, we can write sigma fx equal to 0, which is going to give f minus mg sin theta should be 0, and sigma fy is equal to 0, which will give r minus mg cos theta is 0. Now we are asked to find only the frictional force, so we can only use the first equation, sigma fx equal to 0. From that, the frictional force can be written as mg sin theta. So m is 2 kg, g is not substituted in the solution, so we will keep it like that, and sin of 30 degree. So sin 30 is 1 by 2, so it's 2g times 1 by 2, so 1g Newton. So that is the answer. So option A will be the answer. And if you want to find the normal reaction, you could use r equal to mg cos theta. So if we just evaluate it, it will be 2 times g times cos 30, which is root 3 by 2, so it will be g root 3. Okay, but it's not asked here, so that is a solution. And so any doubt here? Good. So then we'll move to the next problem. So a 70 kilogram pole is on the verge of slipping in a position as given in this figure. Find the coefficient of static friction between the pole and the ground. Assume that the pulley is frictionless and acceleration due to gravity is 9.81 meter per second. So round off the answer to 2 decimal places. So we are asked to find the friction coefficient of static friction coefficient, assuming this this entire setup is in equilibrium. So I hope the question is clear. So we can start doing this. So here is the pole, which should be in equilibrium. So just so the hint is that just try writing all the, try drawing the free body diagram of this pole and do the force balance, that's all. But now we just need to consider the friction also. So you could try this. So I'll give some time for you to try this out, and then I will explain how to do this. Okay. Did you find the answer? Okay, good. So I will explain it. So so basically, that's so what are the forces that is going to act on this pole? So it has 70 kilogram weight. So that is going to act exactly through its center of mass. So mg is going to act vertically downward. Now there is a tension that is going to act along the string. The same tension which is shown here, which is transmitted along the inextensible string. Now what else can happen? It has a contact with the surface at this location. There will be a normal reaction acting from the surface. This much was enough in the earlier chapters. Now we have friction also. So a frictional force will also act along the surface, tangential to the surface, which will be proportional to mu times r at equilibrium. That mu is that what we need to evaluate. Now which direction this can act? So assume that there was no friction on the surface. Now this pole will try to slip. This will try to slip this way, so that now if there is a friction, it's like the pole is trying to move that way and the friction is opposing that motion. So the frictional force should act other way, so that the body will be in equilibrium along the surface. Is that clear? So if there is a doubt, please stop me. So I assume that it's clear. So I'm just going yeah. So now so if I redraw this pole, so we have a reaction force R here and a frictional force F here, mg here, and tension T here. Now this angle is 30 degree, and we may need one more angle. So let's call this angle to be theta. So that I am marking here as theta. If you do the equilibrium, so we have three equations: sigma fx equal to 0, sigma fy is equal to 0, and sigma m equal to 0. So these three equations we need to use for this pole to be in equilibrium. So what are the horizontal forces acting on the system? So first we will see sigma fx equal to 0. So the frictional force is acting horizontally, so that will come. Then R and mg are acting vertical, so that is not going to contribute. And a component of tension, T cos theta component. So if I split T, it will have two components: T cos theta along the horizontal direction, and T sin theta along the vertical direction. So theta is still unknown, we need to evaluate it. But let first finish the equilibrium equations, then we'll go back and see whether we need theta or not. So for the moment, assume theta is a non-quantity. Indeed, we can evaluate what is theta, so we will do that soon. But just assume that theta is already known. So we'll just write the equilibrium equations first. So F and minus t cos theta, they should balance to 0. That is a horizontal equilibrium equation. Now vertical, so from this we can write the frictional force equal to t cos theta. Now the vertical equation is that r is acting upward. Similarly, t sin theta is also acting upward, and mg is acting downward. So minus mg should be 0. So this is another equation. Now the moment we have to equate to 0. So what we can do is that we can take moment about any of the point, whichever point you take, the moment should be 0, like we have done in the previous sessions. So let us take this point P, which is the contact point with the surface. So moment about point P should be 0. So both the friction force F and the reaction force will not cause a moment because they are passing through the point P. Now mg will create a moment, going to create a clockwise moment. So mg times the moment arm. So moment arm is for mg is actually this distance. Remember, let's say it has a length L. It's actually given L is 7 meter. So we will use that later. So if it has a total length L, it is split into L by 2 here and L by 2 here. So and this angle is 30. So L by 2 sin 30 will be the moment arm. So it's L by 2 sin 30 for mg. So this is creating a clockwise moment. Now t will have two components, t sin theta and t cos theta. Both are having an anti-clockwise moment. So that will be like minus t cos theta, which having so t cos theta will have a moment arm which is this distance. So that is going to be L cos 30. Okay, and now t sin theta, which is also going to create anti-clockwise moment. So t sin theta, and whose moment arm is this distance, which is L sin 30, and the net moment should be 0. So any doubt in this this part? So if that is clear, then we can rearrange the last equation, the moment equation. So because the only unknown in the last equation is T, that is the tension in the string, and all other quantities are given. M is known, G is known, L actually we don't need. L is 7 meter, it's given, but L will anyway get cancelled from all the terms, and we can just rearrange. So T cos theta cos 30 plus sin theta sin 30 is equal to mg by 2 sin 30. And if you rearrange, so also you really don't need to use the identity here. You can explicitly evaluate cos theta and sin theta and use that, but because it's looking like the identity cos A cos B plus sin A sin B, which is just cos of A minus B, so it's cos of theta minus 30. I'm just using the identity, you don't really need to use it. So it's mg by 2 into sin 30, and from this the tension can be evaluated as mg sin 30 by 2 cos of theta minus 30. Now we really need to evaluate what is the angle theta, then only we can evaluate the tension. So for that, if you come back to this figure and see the triangle, let me call that as A, B, C. It's a right angle triangle because this angle is 90 degree. So it's theta here, this is B here, A here and C here. The adjacent length to theta, which is just 7 sine 30, this length, because this is the projection of the 7 meter, which is the length of the pole along the horizontal direction, which is 7 sine 30. And excuse me, the projection of the pole along the vertical direction is 7 cos 30, which is going to be the distance PB. Okay, now the total length from P to C, that is this distance, is given as 12 meter. So if we subtract the 12 meter minus this projection of the pole along the vertical direction, that is 7 sine 30, that will be the distance BC. So BC will be just 12 minus 7 cos 30. So I hope that is clear. If it is not, please let me know. So if that is clear, we can write tan theta from this triangle is 12 minus 7 cos 30 by 7 sine 30. So let me evaluate that. So I think it's 1.6965. So if you find a mistake, please let me know. So from this we can write theta, which is tan inverse of this quantity, I think it's 59.483 degree. So we have evaluated the angle theta. So now we can use that here to evaluate the tension. So tension should be mg sine 30. So m is given, which is 70 kilogram. So it is 70 times g, which is 9.81, times sine 30, which is 1 by 2, the whole divided by 2, times cos of theta minus 30. So theta was 59.483 minus 30. So let me evaluate it. So it is 197.214 Newton. So this is the tension along the string. So now we got one of the folds. Now from the horizontal balance equation, that is f minus t cos theta equal to 0, we can evaluate what is the value of f. So f is t cos theta, so which is 197.214 times cosine of theta, which is again 59.483. So I think it's around 100.144 Newton. So we got the friction force. Now we use the vertical force balance equation, that is R plus T sine theta minus mg equal to 0. From that, now the remaining unknown is the reaction force R. So R is equal to mg minus T sine theta. So 70 into 9.81 minus T, which is 197.214 times sine of 59.483. Let me evaluate it. So I think it's 516.804 Newton. So now we have evaluated all the unknown forces acting on this pole. Now our objective is to evaluate the friction coefficient. So for this system to be in equilibrium, F should be, in maximum value of the friction coefficient times R, or from this expression we can write the static friction coefficient is just F by R. So we have F equal to 100.144 divided by the reaction force, which is 516.804. So if we just evaluate it, so we will get the value of the friction coefficient to be 0.1938. So we can round to 2 decimal, which is 0.19. So that's the answer. Is this clear? So then we will move to the next problem. So the below block of weight 50 kilogram is being pushed by a force P applied at an angle 30 degree shown. The coefficient of static friction between the block and the ground is 0.03. The block is on the verge of slipping. Select the correct alternatives. So it's an MSQ, more than one option can be correct. So I have to check all the options and verify which ones are correct and which ones are not. So in the options, if you see P is 500 Newton is given as option A. Again, the last option says P is 450 Newton. So anyway, we have to check what is the critical value of P, so that this is just at the verge of slipping, and make sure is it 500 or 450, which one is correct. Option B, the magnitude of a normal reaction acting on the block is 17 Newton. So we have to evaluate the normal reaction and check whether it is 17 Newton or not. And the third option says that the normal reaction force act at a distance 0.05 from the middle edge of the block. So usually we draw the normal reaction acting through the center R, but here you have to remember, so usually the force will be also acting through the centroid of the system. But now you see this force which is acting not through the centroid, it's at some other distance, so that there will be a moment created which will try to rotate this system, so that the net but it should be in equilibrium, so that the net reaction force should be displaced by some amount from the center, so that this body will still in equilibrium. So what is that distance. So it's given 0.05 meter from the centroid. So we have to verify that is it correct or not. So basically I have to check these three things in this particular system and check which ones are correct and which ones are not. So the P load is acting here at an angle 30 degree with the horizontal, and this is 5 meter. I don't know whether it is clear. It's 5 meter and 3 meter. So 5 meter in length and 3 meter in height. So you can try this out. I'll give you some time for try, and then I will explain how to do this. So in case if you found the answer, please let me know. I mean, we have four options. If you found any of the option is being correct or being wrong, you can just let me know so that we can discuss them. Okay, somebody has raised a hand. So do you have any question? So I think that's a mistake. So basically you just need to draw the free body diagram of this body and just do the normal, the force balance. The horizontal force should be balanced because this is not yet started moving. It's a verge of slipping, so still it's in equilibrium. So the horizontal forces should be balanced, vertical forces, also the moment. So the moment we usually don't consider in every scenario. You may have attempted some of the assignment problems where you really don't need to consider the moment. Here you need to consider the moment because, as I mentioned, the force is not passing through the centroid. If all the forces were passing through the centroid, then you really don't need to worry about the moment, because if you take the moment about the centroid and all the forces are passing through the centroid, so what are the forces that can act here? So one force will be it's a weight, and another is a normal reaction, and they both will pass through the centroid. And now the extra force is the external applied force P. If that also passes through the centroid, then basically you don't have any force which is creating a moment about the centroid. Now because here is friction which will not pass through centroid anyway, so that will create a moment. So you need to consider the moment balance. This entire force system, all the forces should the moment created by all the forces should add up to 0 for that. So for this system to be in equilibrium, so you just need to draw the free body diagram and do the force balance and moment balance. Oh, okay. So I think I mentioned something wrong. So here the weight will anyway act through the centroid. Remember, the normal reaction not necessarily need to pass through the centroid because the loading is not passing through the centroid. So for the system to be in equilibrium, the normal reaction may offset from the centroid to a certain distance, and the third option is actually mentioning that it's offsetted by 0.05 meter. So we have to verify. So assume there is a offset of the normal reaction, and then check whether the offset is indeed 0.05 or it's actually 0. If it is 0, then we can say okay, the normal reaction is passing through the centroid. That's how you should do this problem. Any question? So anyone found any answer? What is the critical value of P or the magnitude of the normal force? So I am expecting you guys are trying this out, and so if you are not, then please let me know so that I will not waste time. I will just explain it directly. Okay, anyway, let me start explain. If someone find the answer, please let me know through the chat box so that we can have a discussion. So as I mentioned, we just need to draw all the forces acting on the body. So it has some mass, 50 kilogram. So the mg will act vertically down through the centroid. But as I mentioned, the normal reaction usually we will draw like this. Should pass through centroid. But as I mentioned earlier, it should now be offsetted by some distance. We really don't know what the distance is. Let us call that distance as let's say L. We'll come back to what the value of L is. I mean, offsetted from the centroid by a distance of L. Or okay, I think it's better we'll measure this distance from this edge and call that as L. Okay, so now if we consider the free body diagram, so the force is acting, mg is vertically downward and r is acting upward, and yeah, p is acting here at an angle of 30. So really if you resolve p, you can have two components here. So p cos 30 will act horizontally and p sin 30 will act vertically. Now one more force is there, that is the friction force. So now that should act parallel to the surface, the friction force. So that force is here. Yes, somebody raised a hand. Any question? I think that's a mistake. So if you have any question, please let me know or type in chat box. So I'll continue. So this is a system. So we'll first do a force balance. Sigma Fx equal to 0. So the horizontal forces are P cos 30 and the friction force F. So they should be balanced. So F should be equal to P cos 30. P is unknown. We have to evaluate that, the critical value. And now the vertical force balance. So the vertical forces acting in the system are P sin 30, mg and r. They should be in balance. So mg is acting vertically down. Similarly, P sin 30 is acting vertically down. Should be balanced by the normal reaction r. Now sum of the moment about any point should be in for equilibrium, this should be 0. So we can take any point. It should be a better point. So we have unknowns, capital R, the normal reaction, P and friction force F. So better we should avoid some of the forces. So let.
Sir, please speak in Hindi.
Sorry, I can't take a class in Hindi because so many have registered and everyone should understand what
Okay, sir. Okay, sir. Continue, sir. Continue.
Okay. I hope you understand. So
okay, sir.
So yeah. So what I was saying is that so we should take moment about any point and it should add up to 0 for equilibrium. So I would choose let's say this point. I'll call that point as O, which is the corner on the right side. So that will be here. Oh, excuse me. This point O. So why I choose that point is so that the moment like you have already experienced this. If I take a moment about that point, the friction force is passing through that point, so that will not create any moment. So the moment creating forces are P cos 30, P sin 30, mg and r. Now first of all, about the point O, P sin 30 is creating an anti-clockwise moment. The moment arm is this distance, which is basically 5 meter. So I will just use P sin 30 times 5. This is creating a counterclockwise moment. Now P cos 30 is creating a clockwise moment. So that will be minus P cos 30 times the moment arm is basically this distance, which is 3 meter. So P cos 30 times 3. Now again mg is creating a counterclockwise moment. So plus mg, which is actually acting through the centroid. So the moment arm should be 5 by 2. This is the distance. So that will be half of the total width of the block, which is 5 meter, right? So that's 5 by 2. Now r is creating a clockwise moment. So that will be minus r times. Now we know the distance through which the r is acting. We really don't know that. So let's call that distance. So I have initially marked this distance as L. Now I deleted that and I say this distance is L. So that r times L is the moment. The moment arm is L. So saying that r is acting L distance from the point O, from the right edge. So this entire moment should add up to 0. So so these are the equilibrium equations. So we have 1, 2 and 3. Now so we have a lot of unknowns here. P is an unknown, F is an unknown, R is an unknown, and L is also an unknown. But now it's given that we have to solve the system at the verge of slipping, so that the system is still in equilibrium, so that it's just starting to move, or just before the motion. So the friction force then should be equal to mu times the normal reaction. So mu s, the static coefficient of static friction, times the normal reaction. So there should be a relation between them. So if we use equation 1, you can write mu s times r is p cos 30, and from equation 2 you can write r equal to mg plus p sin 30. Now if you take a ratio between the both equation, these two equations, you can write mu s, basically mu s into r divided by r on the left hand side, so they will cancel. On the right hand side we have p cos 30 by mg plus p sin 30. Now if you rearrange, you can write mg into mu s, basically cross multiplying, plus p mu s sin 30 equal to p cos 30. Again, our objective is to solve for the unknown p. So p times cos 30 minus mu s sin 30 equal to mg times mu s. From this we can write the p, the critical value of p, so that just before it is start to slip, is mg mu s by cos 30 minus mu s sin 30. And we have m given, which is 50 kilogram, so it is 50 times g is 9.81 times mu s, the coefficient of static friction, is given to be 0.03 between the block and the surface, divided by cos 30. Cos 30 is root 3 by 2 minus mu s is 0.03 times sin 30 is 1 by 2. So if you do the calculation, let me try this. So you will get 17.29 Newton. So that is the critical value of the load. So now if you go back the options, you can see option A says P should be 500 Newton, option D says 450 Newton, and whatever we got is 17 Newton only. So we clearly can say that option A and D are wrong. Now continue. We have to evaluate the so option B is magnitude normal force acting is 17 Newton. So we have to verify whether it is correct or not. So again we can use equation 2 to evaluate the normal reaction R. So R is mg plus p sin 30. So m is 50 times g is 9.81 plus p is evaluated just now 17.29 times sin 30 is 1 by 2. So let me evaluate that. So that is 499.145 Newton, approximately 500 Newton. And option B says that it should be actually 17 Newton, so that is also wrong. Okay. Now the option C only remaining. The normal reaction force acting at a distance of 0.05 meter from the middle edge of the block. We have to verify whether it is correct or not. So for that, we have to find through where the reaction force R is passing. So we have to use the third equation, the moment equation. So from equation 3, we can write R times L equal to 5p sin 30 minus 3p cos 30 minus 5 by 2 mg, or the distance L, which is, if you rearrange it, is evaluated by this expression, can be. So if we substitute them, 5 sin 30, which is 1 by 2, minus 3 cos 30, which is root 3 by 2, the whole multiplied with the p. So what I did is that I just taken the p outside from these two expression and put it outside the bracket. So it is 17.29 minus 5 by 2 times m times g. So what was m? 50 kilogram. So 50 times g is 9.81, the whole divided by R, the normal reaction that we have just evaluated, which is 499.145. So if you evaluate, we will get the value of L. Let me evaluate that. Did I made any mistake? So moment equation is p sin 30, which is acting at a distance 5 meter counterclockwise. P cos 30, which is acting at 3 meter clockwise. R is acting at a distance L, which is creating a moment R times L, which is also clockwise. Mg is acting at distance 5 by 2. So mg into 5 by 2 is also counterclockwise. So I think that is correct when I rewrote it. So R times L is P times 5 sin 30 minus 3 cos 30. Yeah, so there was a mistake. It's a plus 5 by 2 mg. So this should be plus here. Okay, now let me evaluate. So the answer L is 2.4533 or 453 meter. And so this is the distance from the point O measured in the left direction. Now, but in the option C, it's given the distance measured from the centroid, the middle edge of the block, that is basically this distance. And this distance, it's called that distance as x. That, if you see, it's the total length of the block is 5 meter, so that x plus L should add up to half of the length, so it will be 5 by 2. So the x should be 5 by 2 minus L, so that is 5 by 2 minus L, so that is 2.5 minus 2.453, so that is 0.0467 meter. On approximately it's 0.05 meter. So I think we have used the value of G to be 9.81. If we have used the value to be 10, then we would have got everything like 17,500 and 0.05 as a value. So I think the option C is correct in that sense. If we have used G to be 10, we would have got 0.05 meter. So yeah, that is correct actually. Option C is correct. So is this clear? Any questions? So basically we are writing the equilibrium equations and just solving for the unknowns. So we have to write, it's similar to what we have done earlier, the force balance, horizontal and vertical, and moment balance. Just that right now we have one more force, that is the friction force, and which has a limiting value which is equal to the coefficient of friction times the normal reaction. So that's all. So I hope this is clear. So we'll move to the next problem. So determine the minimum static friction coefficient between the spool and the wall. So we have to find what is the friction coefficient between the spool and this wall, such that the 20 kilogram spool shown in this figure does not slip. So round off the answer to 2 decimal places. So like earlier, you just need to first draw the Freiberg diagram, all the forces acting on it. So if you know how to do it, you just start doing it. So I'll give you some time for you to try this out, and then I'll explain. If you found the answer, you just let me know. We will discuss that. Anyway, I will solve this, but let me give you some hint so that you can try this out. So the forces acting on the system, normal reaction will be acting from the wall. I mean the system in the sense that I am talking about the spool. Okay. So it will have a tension along the string. It's on weight through the centroid. Then a normal reaction from the wall. And because now we have friction also, there will be a friction acting tangential to the wall, which is trying to stop the motion. So basically, if there was no friction, this spool will try slipping through the wall or move along the wall, and friction is trying to stop the motion. So the friction will act in such a way that it will restrict the motion. So those are the forces acting. You just need to do the force balance and moment balance to solve the problem. So you can try this out, and then I'll explain how to do this. So if you don't need time to try this out, you can let me know so that I will just directly explain it. But I just want you to try this. Um, yeah. So I know this time is not enough for you to try this fast, but because we have time constraints, that's why I'm asking. Anyone found the answer? So let me anyway start explaining. So if you found the answer, you can let me know. So I'll just draw the free body diagram of this spool. So we have um, let me redraw it. Yeah, I think that is better. so so this is Android. So its weight is acting vertical down, mg, and tension is acting along this string. Now from the uh, wall there will be a normal reaction acting, and because the gravity is pulling, it is trying to move downwards, so that the friction will be opposing through the wall this way. So these are the forces acting on this system. That's all. Just need to do the force balance, moment balance. That's all. So we'll start doing that. So we have horizontal forces R, vertical forces mg and f, and an inclined force T. So which will have two components. So T cos theta and T sin theta, where theta is an angle. So you can see this angle, this theta, and if you join complete this triangle, you will know theta should be 70 degree. So the component forces are so this is T cos 70 and this is T sin 70. This angle is 70 degree. Okay, so now we need to write the force balance equation. sigma fx equal to 0. So that means T cos 70 should be balanced with um, the normal reaction R, so which is the first equation. And the vertical force balance equation, which is T sin 70, and the friction force F should be balanced by the weight mg. So which is equation 2. Now we need to write the moment balance equation. So moment about any point should be 0. So just to eliminate together the friction and the reaction, which are the unknowns, I would choose this point, the contact point with the wall, the O. So that moment about O should be 0. That's our objective. So if we evaluate the moment about O, what are forces creating a moment? Give me a second. Okay, so the friction force F and the normal reaction R are passing through the point O, so they are not creating any moment. The force mg, which is going to create a moment, which is creating mg times the moment arm, which is this distance, right? So if you see, it's given that distance is 0.5 meter, the radius of the outer circle. I would call that as let's say R outer. Okay, I mean R outer is, we know it's 0.5 meter, and the inner circle radius Ri is 0.15 meter. We'll substitute them later, just I use the notation right now. So the moment arm for the force mg is R out, so it's R O, and this is creating a counterclockwise moment about the point O. Now T cos 70 and T sin 70 both are creating clockwise moment. So let us first write T cos 70. So which is creating a clockwise moment. Now the moment arm for this T cos 70 is actually so if you see, the line of action of T cos 70 is this. So let's say this distance, which is let us call distance y. Okay, so that y distance is unknown. We had to evaluate the y value. So for the moment, we'll just write y. And now T sin 70, which is also creating a clockwise moment. So T sin 70, and which is line of action is actually this, and that is not exactly passing through the center or centroid. So which is actually not exactly RO, but a little bit more than RO. So let us call that distance from the point O to be x. That is the moment arm. That is also an unknown. So for the moment, let's call that as x, and this is a total moment, and this should balance to 0. So now this is equation 3. So the unknowns in the equation 3 are T, x and y. So I mean, actually x and y are known, but we wrote in an unknown way. We have to evaluate x and y in terms of known variables. If we know that, then we can directly solve equation 3 to obtain the unknown T. Remember, RO is already known, it's 0.5 meter. If we know T, then we can go back to equation 1 to evaluate R, the normal reaction. Then use T and R to evaluate. So okay, so what is asked to evaluate? Okay, we are asked to evaluate the friction coefficient. So if we know R and T, then we can come back to equation 2 and evaluate the friction force F, and the ratio of friction force to the normal reaction should give the critical value of this friction coefficient, so that this pole will not slip. So that we will do. So we have to start from equation 3, and first we have to identify what is x and y in terms of the non-parameters. So it is basically a geometric thing. So we'll just do that here. Let me draw the circle again. Now this time this is the inner circle. I just want to draw this a little bigger. Yeah. So this is the center line, and we have the point here. This is the point through which the tension force is acting. Now we want to find the horizontal and vertical location of this point from this point, which is O. So from O, what is the vertical value, which is this distance, which is y, and the horizontal value, which is this distance, x. These are the two things that we need to evaluate. So let me draw this connection from the centroid to this point. Okay, let me call that point as P. P is the point where the string is attached and string is passing tangential to that point. So basically this angle is 90 degree. It's actually tangent, right? So if that is 90 degree, so we know with the horizontal it is making 70 degree, and the total angle is 90 degree, which means that this angle should be 20 degree, and that would mean this angle is also 20 degree. So let me write that along. So this angle should be 20 degree, and see this is actually R inner, the radius of the inner circle. From P to the point in the center, the length is actually R inner, the radius of the inner circle. So now if you see the projection of R inner along the vertical direction is just y, right? So you can just see y is R inner times sine 20 degree. So I hope that is clear. The projection of R inner in the vertical direction is just y. Now the projection of R inner to the horizontal direction plus the R outer. So the projection of, okay, let me give a name to the triangle. Let's say this is A and this is B. So now let me repeat again. The AP is R inner, the radius of the inner circle. Its projection along the vertical direction is BP. BP is equivalent to the vertical distance y we want to know. So that is why y is R inner times sine 20, which is the projection. Now again the projection of AP in the horizontal direction is AB. So along with the AB, if we add AO, which is the radius of the outer circle, so if we add the both RO plus RI cos 20, we will get the unknown x value, which is OB. So I hope that is clear. So now we know x and y in terms of the non-parameter R inner and R outer. We can go back and substitute in equation 3. So from equation 3, if we rearrange equation 3, we will get t times y cos 70 plus x sin 70 equal to mg times R outer, or the tension in the string should be mg times R outer by y cos 70, where y is R inner sine 20, and now we have cos 70 also, plus x times sine 70, but I am replacing x with R outer plus R inner cos 20 multiplied with sine 70. So the tension in the string is mg R outer by R inner sine 20 cos 70 plus, so you have R inner sine 20 cos 70 time here. Again, if you see R inner cos 20 sine 70 time is here. So if you do the full algebra, I mean, you really don't need to do that. You can just evaluate them. I mean, you can but simplify this further. So you can write R inner taking commonly outside times sine A cos B plus cos A sine B, which is sine of A plus B, right? So that's sine of 20 plus 70, which is just sine 90, which is 1. So that is just R inner will come, plus R outside, the remaining R outside times sine 70. So that's R outside times sine 70. So now if you put all the values, the mass was 20 kilogram, so it will be 20 into 9.81 times R outer. R outer was 0.5 meter, so it is 0.5 by R inner, which is 0.15 plus again 0.5 times sine 70. So let me evaluate it. So the tension in the string, we can evaluate it to be 158.265 Newton. So we got tension. Now if you go back to equation 1, we can evaluate the normal reaction R. So the normal reaction R is T cos 70, so which is T times cos 70. So we know what is T, which is 158.265 now times cos of 70. Let me evaluate that. So which is 54.12 or 13, okay, 13 Newton. So that also we have evaluated. Now from equation 2 we can write what is the friction force. So friction force should be mg minus T sine 70. So which is 50 times 9.81. Okay, mass was 20, right? Yeah. 20 times 9.81 minus tension is 158.265 times sine 70. So So we'll get 47.4795 Newton. So we have got the friction force, normal reaction, everything, and the tension also. Now for this to be not slip, the maximum friction coefficient, so which should satisfy this relation, the friction should be equal to the coefficient of static friction times the normal reaction. From this we can say the static friction coefficient should be at least F by R. So this is a minimum friction required for this to be not to slip. Friction can be greater than this, but this is the minimum value. So this is 47.4795 divided by 54.13. So yeah, which is 0.877. So that's the answer. Is it clear or any question?
Clear.
Okay, so good. So we will move to another problem. So I think this is easier one. So we'll move to another problem. Yeah. So a block of 10 centimeter times 10 centimeter in the base area and height is 15 centimeters kept on an inclined plane. The coefficient of friction between them, the surface and the block is root 3, 1.732. The inclination theta of this inclined plane from the horizontal is gradually increased from 0 degree. So you have to correct. Okay, this is basically saying that 0 degree inclination is increasing from 0 degree. So what will happen? So there are 4 options given. This is an MSQ type question. So at 30 degree the block will start sliding down the plane. One option, the block will remain at rest on the plane up to certain theta and then it will topple. Then third option says at 60 degree the block will start sliding down the plane and continue to do so at higher angles. And the last option says at 60 degree the block will start sliding down the plane and on further increasing theta it will topple at certain theta. So what do you think will happen, or what are the things are expected to happen? So I think understand the situation. We have the block at an angle, basically at an angle theta. So we are increasing the theta value gradually from 0 to upwards. So what will happen to this? So any idea? So I want this to be an interactive session and nobody is responding. It's actually easy question, right? So you can just tell what is going to happen. So basically we are expected that it will start sliding, right, after a critical value. So if the tan theta is greater than the friction coefficient, then it's supposed to slide down. So that's what usually we expect. So here if you see the critical value of theta, which is tan inverse the friction coefficient, which is root 3, so which is 60 degree. So we should ideally see that this block will start sliding after the angle 60 degree. So below 60 degree the block will be stable. Let's say at 30 degree it will be stable, it will be in equilibrium, and again start increasing, still stable. At 60 degree it will reach the maximum friction value, and after which the friction is not able to sustain the downward force, so it will start sliding. So the option C, at 60 degree the block will start sliding down the plane and continue to do so at higher angle. So if you have higher than 60 degree also, it will continue to move. So that's what expected solution. But here is a catch. So this is okay when the block is flat kind of thing, like aspect ratio is more in the horizontal direction. So here one issue that may come is that because toppling can happen, that we need to consider. I don't know whether you know what topple is, topple motion. So so that you may understand if I draw the body correctly. So it has a base of 10 times 10. So we are doing 2D projection of that doesn't matter. So it's have a base of 10 units, 10 centimeter, and a height of 15 centimeter. So the body will be looking something like this. So now you may understand what is toppling. So it has a center of gravity here, through which its weight mg is acting. It will have a normal reaction passing through the center. Now if you increase the angle theta, you may identify what, you can do a thought experiment, you will understand what will happen. About this point O, it can actually have a rolling kind of motion. That's called toppling motion. I don't know whether you understood. Like about this point, can have this kind of, the body should be perfectly rigid, but when I drawn, it's gone bad. So it should not deform. What I want to say is that it will just topple like this. Then it will just roll to the other side. So this can happen if the aspect ratio has a vertical length which is much higher. So when this happens is that the critical point at which it happen is that, so at some angle theta topple, it will try to topple. At that instant, what will happen is the weight which is acting vertically downward, right, which will actually pass through this pivot. This is the pivoting point, right, about which is try to topple. So that this angle is also theta topple. So this is the condition. So this is a critical moment. Beyond this value, this will try to topple. Now how will we evaluate the theta topple? So this is purely just a geometrical parameter. So you can see tan of theta topple. This has nothing to do with friction. Of course, friction is trying to the body not to slip along this line. If friction should be there, but along with that, if theta topple become less than theta friction, that is a critical value which is 60 degree, then it will first topple. It will not first slide. It will start to topple even before sliding. So that's what I have to first evaluate what is theta topple. So if you just consider this triangle OPQ, you can write tan theta is just OQ by PQ. So OQ is just uh, the base width by 2, and PQ is the height by 2, where this is the base width of the block and this is the height of the block. And if you cancel the 2, you will get it's just B by H. Now you can say theta topple is tan inverse of B by H. Now we have base width is 10 and height is 15, so it's just tan inverse of 10 by 15, or tan inverse of 2 by 3. Yeah, and let me evaluate that. That is 33.69 degree. So we have found the theta topple is lesser, which is 33 degree. So what will happen is, and the critical values or the friction, I mean the block to overcome friction and start to slide is 60 degree. So we have two angles. So now imagine we start to start to rise the inclination of the plane from 0. So when we reach 33 degree, it will start topple. It will not start sliding, because for sliding to start it has to reach the 60 degree. But when it reaches 33.69 degree, it will be still in equilibrium in terms of friction. It will not slide, but it has a toppling effect because of the moment it is experiencing, and it will start to topple. So there won't be any sliding happening. It will immediately topple at angle 33. So that's what we have to expect. So the block, so if you see option A, at 30 degree the block will start sliding. So that won't happen, because to sliding it should at least reach 60 degree. So option A is wrong. Now the second option, the block will remain at rest on the plane up to critical angle theta, and then it will topple. That's what the option is. The critical value we have found, it is 33.69, after which it will topple. And at 60, okay, option C, at 60 degree the block will start sliding down. That is true, but here it won't happen, because toppling effect will be dominating. So it will first topple. So the option 3 is not correct because of that. Now at option D, at 60 degree the block will start sliding down the plane. On further increasing theta, it will topple. So we have found the toppling angle is lesser than this friction angle, so that's why it's first topple. Okay, so that's why it won't slide and topple. It will first topple and then it will move down. So option D is correct. So any question on this? Is this clear or? Okay, so I hope this is clear. So I have some more problems. This one is actually easier one. So an 80 kilogram man walks on the rooftop of a dome from the center to right, and if the coefficient of friction between shoes is 0.6, determine the angle theta at which he will start to slip. You can just evaluate the friction coefficient to be just tan of the angle. So 0.6 is tan of theta, and you will get theta is tan inverse of 0.6. So it's fairly simple. Similarly, this problem, an insect crawls up hemispherical surface very slowly. So here also same concept is coming. So we have to evaluate what is the angle alpha above which it cannot rise. So again the friction coefficient will come into play. So here the friction coefficient 1 by 3, So you will find tan inverse of 1 by 3 as the answer. So these are fairly simple problems. So I have this is also fairly simple. So I don't have time to discuss all these things, that's why. So if you anyway, I will upload this. If you want to try this, you can take a screenshot and try solving this yourself. So it's fairly simple actually. You have force F which is acting at an inclination 60 degree, which on a mass of √3 kilogram. Friction coefficient is also given. So what is the maximum value of force so that the block does not move? So after a critical value of force, it will start moving. So what is that maximum value up to which the friction will oppose the motion? It's fairly simple. The first principle, just the force and moment balance. Actually here moment balance is not needed, only force balance is needed. Now another problem. This is little involved, but you can still solve it. You have two bodies, let me call that as A and B. So you have to draw free body diagram of A and free body diagram of B. A has a inclined contact with the surface, with the outer surface, and then A is also has a contact with B. Now B has again a contact with A and another contact with the outer surface. So you have to consider all the reaction forces between. So you have to draw two separate free body diagrams for A and B. Draw the reaction forces, also friction forces. So you have to evaluate what is the least force, so that will cause the motion between the blocks. So it's like the at the verge of the motion, what should be the minimum value of force applied so that they will start moving. It's the same idea here also, but here you have two separate bodies. You have to consider the free body diagram of these bodies separately. Remember, the friction coefficient is different on different surfaces, that's given. So you could try this. I don't know what exactly is the answer, so I will try to upload this with the answer. So any other questions? So then we will end for today, and we'll meet next week. Thank you.